of simple harmonic oscillator. What is the example of simple harmonic oscillator? Okay, a spring and mass system. First example, a spring and mass system. First example, a spring and mass system. Mass system. A spring and mass systems. Okay. First is a spring and mass system, okay, and the second is simple pendulum. Second is simple pendulum. Simple pendulum. Third is first is spring and mass system. Second is simple pendulum. And the third is compound pendulum. Compound pendulum. Compound pendulum. And the fourth is torsion pendulum. Torsion pendulum. Torsion pendulum. Fifth is Helmholtz resonator. Helmholtz resonator. And sixth is LC circuit. Seven is vibration of a magnet. Eight is two masses connected by a spring. Two masses connected by a spring. Nine is bifilar oscillations. Bifilar oscillations. And 10 is bifilar oscillations. And 10 is Then there are some of the examples of a simple harmonic motion. First is a spring and mass system, simple pendulum, compound pendulum, torsion pendulum, Helmholtz resonator, LC circuit, vibration of a magnet, two masses connected by a spring, and 9 is a bifilar oscillations. Okay. Then we will be study about all the examples of a simple harmonic oscillators. Okay. Then first is a spring and mass system. First is a spring and mass systems. First is a spring and mass system. A spring and mass system. Okay. Mass system. A spring and mass system, we will be study about a spring and mass system. Okay. Then you can let this is the base, rigid support. This is the rigid support. And this is the spring. This is the spring. Okay. Spring. This is the spring, and this is the mass. Spring, and this is the mass. This is mass. Okay. This is mass, and this is a weight mg, and displacement y. Okay. Then This is spring, okay? Consider a simple spring. Consider a simple spring whose supported end, whose upper end is fixed to a rigid body, whose upper end is fixed to a rigid body, a rigid support, and the lower end is attached to a mass M. Suppose the spring is extended through a distance. Suppose the spring is extended to a distance L. Say due to distances L or Y, says due to the weight of mg, due to the weight of mg of the mass, then a linear restoring force, then a linear restoring force, linear restoring force equal to S multiply L at once comes into play in the opposite direction. S into L at once comes into play in the opposite direction, okay? Opposite direction. The equilibrium position is attained when these two forces balance each other. Mg equal to S multiply L for equilibrium, okay? Okay? Then S equal to mg upon L. S equal to mg upon L. Okay? Where S is the force constant. S is the force constant or stiffness of the spring, stiffness of the spring, okay? Stiffness of the spring, okay? If the mass be now pulled down through a distance y, from the equilibrium position, the linear restoring force F, linear restoring force, F equal to mg, minus S L plus y, linear restoring force mg minus S L plus y, okay? Then F equal to mg minus the value of S is mg by L plus y, okay? L plus y. Then F equal to mg minus mg by L into y, okay? Then F equal to minus mg by L into y, that is minus sy, then F equal to minus sy, okay? F equal to minus sy. Then if d square y upon dt square be the acceleration set up in the spring, then if d square y upon dt square be the acceleration with the acceleration set up in the spring, set up in the spring, set up in the spring, then md square y upon dt square equal to minus sy. md square y upon dt square equal to minus sy. Okay. Then this is d square y upon dt square equal to minus s by m into y equal to minus mu y. Okay. r d square y upon dt square plus mu y equal to 0, where mu equal to s by m equal to acceleration per unit displacement. Acceleration per unit displacement. Acceleration per unit displacement. Okay, where mu equal to s by m, okay, mu equal to s by m, acceleration per unit displacement. This is the differential equation of mass suspended from the spring. This is the differential equation of the mass suspended from the spring. Then d square y upon dt square is directly proportional to minus y. Okay. Thus linear acceleration is directly proportional to its linear displacement. Okay. Thus linear acceleration is directly proportional to its linear displacement. And is directed oppositively to it, and it's directed oppositively to it. Thus a linear acceleration is directly proportional to its linear displacement and is directed oppositively to it. Okay. Hence mass m attached to a spring executes a simple harmonic motion, and its time period is given by, and hence oppositively. Okay. Hence mass m attached to a spring executes simple harmonic motion, and its time period is given by T equal to 2 pi under root of 1 by mu, under root of 1 by mu, that is 2 pi under root of m by s. Okay. Thus, a linear acceleration is directly proportional to its linear displacement and is directed oppositionally to its. Hence, mass m attached to a spring executes simple harmonic motion, and the time period is given by t equal to 2 pi under root 1 by mu, that is 2 pi under root m by s, that is 2 pi m by s, and frequency n equal to 1 by t, that is 1 upon 2 pi under root of s by m. Okay. Stiffer spring. When we use a stiffer spring of spring constant s dash, such that when we use a stiffer spring of a spring constant s dash, such that s dash is greater than s, then t dash equal to 2 pi under root m by s. Okay. As s dash is greater than s, then t dash is less than t. The time period will be decreases. The time period will be decreases. The time period will be decreases. Okay. Dimensions are force constant. Next is dimensions of a force constant. Dimensions of force constant. Okay. What is the dimensions of a force constant? Okay. What is the dimensions of force constant? Okay. Consider a mass m attached to a spring executing simple harmonic motion. If y is the displacement of the mass from its equilibrium position at any instant of time t, then the restoring force F acting on the mass is given by F equal to minus Sy, where S is the force constant or stiffness constant. The stiffness of the spring. Okay. Dimensions of S. Dimensions of S are F upon Y, that is force upon displacement. Force upon displacement, that is the dimensions of force is m1 L1 t to the minus 2 whole upon L1. Displacement, the dimensions of displacement. Okay. Then L1 is cancelled out by L1, then that is m to the power 1 and t to the power minus 2. Okay. Then stiffness is expressed in newtons per meter. Then stiffness is expressed in newton per meter. Okay. And m inverse. Okay. And m inverse. Okay. And next example is Next example is simple pendulum. Okay. Next example is simple pendulum.